But yeah, we're really excited to have Alex here today. So there's a little bit of background. Alex is a is a research scientist at Facebook, or Meta, sorry, my bad. And before that, he did his PhD at INRIA, and he's worked on a lot of really interesting topics like memorization in machine learning models and also watermarking. But today he's going to talk about something else that he's worked extensively on, which is like privacy attacks and how you analyze privacy leakage in machine learning. So yeah, the virtual floor is all yours, Alex.
Thanks, Jamie, for the intro. And hi, everyone. So today I'm going to present this paper called Membership Inference Bounds for the Sample Gaussian Mechanism. This is joined to work with Said, who I think just joined, Graham Carlo from Meta, and Somesh Jha from Wisconsin University. So as I said earlier, if you have any questions during the talk, feel free to interrupt me directly to discuss them. Right. So this is I guess, a general slide of context. So we know that models are getting bigger and bigger, and in recent times we've seen a very sharp increase in the number of parameters. They are getting to billions, tens of billions, hundreds of billions, even I think the next order of magnitude, which I don't know what it is, trillions maybe. And these models have the capacity to memorize a lot of information. So a funny computation is that if the number of parameters is equal to the number of tokens for a language model, which is the case for, at least in the ballpark, for most of these recent extremely large language models. And the loss is like rather low. So here I reported 2 nats per token, which I got from the Chinchilla paper from DeepMind. But I think different, like other language models should have similar loss. It means that you could technically store the training set itself in the least significant bits of the parameters. So it means that if you were to do that and modify a language model, then the language model would be able to spit out the whole training set if you like exactly. Of course, this is not what happens in practice because people train these models in the usual way, which doesn't, to the best of my knowledge, involve putting the actual tokens in the least significant bits. But the thing with privacy is that we cannot rule out that some information finds its way through the parameters of the model. So there has been some work in particular on reconstruction attacks on language models. I think one of the iconic ones from the last few years is the secret share by Carlo et al. Here they showed that language models memorize particular information, which I think was quite new in like conceptually, because people sort of assume that language models would just learn about the general structure of language and the general facts, but they would not focus on particular information such as credit card numbers or phone numbers or any like particular thing. But in this paper, they show that if you actually insert these canaries in the training sets, as shown here, so typically something like the random number is blah, 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 the model will actually learn these canaries in the sense that it will assign them a higher probability than the same sequence, but with other random numbers. And this means that you can find the secret by just prompting the language model. So in more recent years, there has been an adaptation by the same group of this attack to a more realistic one on language models. So it's the training data extraction paper. So now, instead of using these canaries, they are taking a real-life language model, GPT-2, and they show that similar techniques can be used to prompt basically the language model and find verbatim sequences from the training sets. And even sentences that appear only once can be memorized. So sentences that are not duplicates in the training sets. So more generally, I guess, we like in the field, like the field has converged, I would say, on testing the privacy preserving or non-privacy preserving capabilities of models by using this membership inference type of attacks, which were coined by Chokri et al. In 2017. The general idea is that you have a large pool of data that you split between a training set and a held out set. You train a model on the training sets, and then you sort of like mix the data together. And the purpose of the attacker is from the learned model and from this like mixed together data, figure out which data points were from the training set and which data points were from the held out sets. I should also note that in general, the attack is done on each point individually. So you're not considering the whole set, which might give you information from one data point to another. So there are multiple ways then to measure the performance of an attack once you do that. So it's, I guess it's a typical binary classification problem, but here like instead of being cats versus dogs, it's like members versus non-members. So one kind of metric is this like average success rate or advantage. So the success rate, so let's say that you have a 50% prior that the sample was included in the training set. The success rate of an attack, so a random attack that guesses at random will have like a 50% accuracy, and the perfect attack will have 100% accuracy. So you can rescale that to be between 0 and 1. So that's like, I guess, the average advantage metric. And you can also measure the precision recall or the true positive versus false positive rates of the attack. So this is typically the work that we did with my intern last year, Lauren, that you can see here. So we did these loss attacks and the calibrated loss attacks. And you can see that on the right plot, it's pretty telling. One of them has a much higher precision than the other. And if you only look at the model that has the best, at the attack that has the best accuracy, it's at a point where it sort of hides the precision and the recall. And so in the, I guess, the last year, there has been a shift in the community of practical membership inference attacks, sort of away from average and advantage type metrics towards this precision recall or true positive versus false positive. And there is also this seminal paper by Carlo et al., membership inference from first principles, where they look at true positive versus false positive rates with log-log plots. So you can basically focus a lot on the members on the high precision attacks. So basically these attacks only reveal a couple of samples, but they are super precise. So how do we defend against these attacks? Of course, the crowd at this seminar probably already knows everything about this. So differential privacy is the traditional way of defending against these attacks. So in differential, like we say that a mechanism M is epsilon delta differentially private if basically when we have two data sets D and D prime that only differ by one sample, the probability that the mechanism outputs something under D is less than or equal than exponential of epsilons times the probability that this happens under D prime plus delta. So in practice, we achieve, like we know of some epsilon delta differentially private mechanism, such as noisy SGD. So I won't go into the details here, but noisy SGD or DPSGD is the tool that most people use to train deep learning models with differential privacy. And in general, DP is the universally accepted standard for privacy, and there's a bunch of reasons for that. In particular, DP has many nice theoretical properties. And in particular, there is this property. So if you do these membership inference attacks, you can relate the true positive rate and the false positive rates of the attack to the epsilon and delta from differential privacy. So there are, like, I think, two axes. One is theory versus practice, and the other one is the metric that you care about. So either average case or what I call the 1 minus delta worst case. Well, it should probably be the delta worst case, but it's basically you can say that nothing higher than this occurs with probability 1 minus delta. So if you look at the first left corner, the theory and the 1 minus delta worst case, this is exactly the epsilon from differential privacy. If you look at the row below, so the practice with the 1 minus delta worst case, that corresponds to this latest membership inference attacks that look at precision recall. And if you look at the right side of this table, of course, this is a sparse set of references, so I'm obviously missing a very big deal of references. But on the average case with practice, this is where the traditional membership inference type of attacks lie, such as the one that by Shock et al. And the last case, which is the top right case, is how do you have theoretical bounds on differential privacy, but instead of being for the 1 minus delta worst case, you now care about the average case. So there is work that has been done on that, including Alexandre et al. And Humphries et al., and also Yeom et al. That I'll show in the next slide. In the next slide, I guess. And so basically, we know that the epsilon from DP is tight. This is the work by Nasser et al. On the adversary instantiation that they will also show later. And the purpose of our work was to look at whether the bounds for DP on the average case were tight. And we actually get, so we get better bounds than the ones that existed before for the particular case of noisy SGD, so the sampled Gaussian mechanism. And we show that these bounds are tight. Okay, so this is, for context, this is the adversary instantiation work. In this work, they compared the theoretical epsilon to the empirical epsilon that you get from the Kairos bound. So if you derive epsilon from the true positive versus false positive rate, you get an empirical epsilon, and you can compare that to the theoretical epsilon that's given to you, for example, by Régnier DP accounting. And in the paper, they show that in the most adversarial setup, that's sort of corresponds to the hypothesis allowed by differential privacy, you get an empirical epsilon that's very, very close to the theoretical epsilon. And I think that in the meantime, the theoretical epsilon bounds have been revised. So, but they have been revised by a very small amount. So we still have this tightness. All right, and for the bound on the average case, there was initially a bound proposed by Yeom et al. In 2018, which bounds the advantage by exponential of epsilon minus 1. So like all of these bounds, as you can see on the right plot, the advantage goes to 0 as epsilon goes to 0. So that's nice. And they all go to 1 as epsilon gets bigger and bigger. But the problem of the bound by Yeom et al. Is that it has an exponential dependency on epsilon. So of course it grows very quickly and sort of like goes off. And it goes off at epsilon equals 0.3, well, okay, maybe something like that. And this is extremely small. Like I think I would tend to say that in practice, people agree that a good range for epsilon is between 1 and 10, approximately. So if your bound starts to be vacuous before 1, basically you're not happy. So this bound was refined further by Alexandre et al. In 2019. Here they have a much better dependence in epsilon. And we can see that it like doesn't blow exponentially, and it actually smoothly converges to 1. And this bound was even further improved later by Humphreys et al. In 2020, which gives yet a better bound. And basically, our goal in this paper is to further refine that bound. So a bit on the setup. In this membership inference game, we assume that the trainer flips a coin B and will decide to train on either dataset D if B is equal to 0, or dataset D prime, which is the union of D and another sample Z prime, if the coin flip bit is equal to 1. The adversary observes all the training steps S0 from ST. So we assume that there are T training steps. And I guess this is very important because this is not very usual. So it means that the adversary has access to all the gradients that were taken at all the intermediate steps. So I want to precise that these are the average gradients. And in the case of noisy SGD, is the average and noise gradients. And basically, the adversary will then compare the transcripts. So I call that the transcript when B is equal to 0 versus the transcript when B is equal to 1. And the idea, of course, is that if you include this sample Z prime, the gradients will look a bit different. So we should be able to pick on the signal to conduct the attack. Based on that, the adversary estimates the coin B prime, and the metric is the advantage. So I'll show that later, but it's basically twice the probability that B is equal to B prime minus 1. Okay, and on the other side, we have the defense. The defense is the sample Gaussian mechanism. So here I show the difference between regular SGD and DP-SGD. As you can see, it's not very different. So the first difference is that instead of taking the samples batch by batch, so what we usually do is that we shuffle the data sets and then we go over this data set batch by batch. With DP-SGD, you have to do Poisson sampling, which means that you choose to include each sample independently with probability Q. And instead of taking just the average of the gradients, we take the average of clipped gradient and add Gaussian noise. So in blue is the clipping plus noising operation. And what is highlighted in green is the per sample gradient. So it's actually slightly more complicated in practice if you want to implement that, because these per sample gradients are not given to you by classical frameworks such as PyTorch, but I won't go into these details here. So the objective is to bound the advantage, to have a better bound for the advantage. And here I show a quick look at the results that we'll have at the end of this presentation. So on the x-axis, we have the epsilon at delta equals e to the minus 5. And we have the corresponding sigmas on the x-axis on the top. And on the y-axis, we have the advantage that's given by multiple bounds. We have the bound by Humphreys et al. We have our Pinsker bound that is better, but also tends to go off sort of quickly. Then we have our bound in red, and we have the empirical evaluation in green, and we can see that these two match closely. The left plot is without subsampling, and the right plot is with subsampling. So in both cases, we have the tightness of the bound. Okay, so we'll consider these two distributions x and y, or they are well, these two random variables x, y are their distributions mu and nu. And the attack consists in predicting that a transcript comes from x. The data set comes from x if the transcript is in A, which is a region of space. Otherwise, it comes from y. So on the right, I just showed again the computation to go from the success rate to the advantage. So the success rate is half of probability that X is in A plus probability that Y is not in A, which this probability of Y not being in A is 1 minus the probability that Y is in A. And so you can see that the success rate is is 1/2 of 1 plus the advantage, and the advantage is this probability that X is in A minus probability that Y is in A. And this advantage is actually the measure under mu of this set A minus the measure under nu of this set A. And so the advantage of the optimal adversary is the soup over all these sets of the advantage for one region of space. And this turns out to correspond to the very definition of the total variation between random variables X and Y. So our goal here is to find a better bound for this advantage. So we want to find a better bound for this total variation. So before we dive in, I just recall a couple of properties of the total variation. So it can be shown that the total variation is half of the soup over all function from the space to real values between -1 and 1 of integral of f under x minus integral of f under y. In particular, if and if you have a function g, in particular, you'll have that the TV between g of x and g of y is upper bounded by the TV between x and y. And so if g is a bijective transform, then the total variation actually gets conserved if you apply this inequality twice. Okay, so now that you have seen that this problem boils down to bounding the total variation, we can use Pinskell's inequality that bounds the total variation by the Kolbeck-Leibler divergence. So that will be our first bound. And as you saw in the plot earlier, it's already better than the bound proposed by Humphreys et al. But we want to get to a tighter bound. So I will explain in a minute how we do that. But first, I want to insist on the main issue to sort of get bounds in general for this Gaussian mechanism. So the problem is that each step is conditionally Gaussian, because each step, given the past, takes a gradient and adds noise, Gaussian noise. But the problem is that a combination of two steps, so if you look at the output of the second step, this distribution is not marginally Gaussian. It's conditionally Gaussian given its past, but it's not marginally Gaussian. Because when you take a step, you modify the gradient for the next steps. And this is sort of where the non-linearity or the non-Gaussianity kicks in. So the proof idea, in a very loose sense, is to show that the worst case scenario is actually inconditionally Gaussian. And for that, we'll need this main ingredient, which is the TVA. So for random real value, well, for real value A, we define the TVA. So the difference between the TV and the TVA is that the TVA has this A factor between the distribution of Y. So TV1 corresponds to the TV, but in general, it's like a different, I guess, metric between two probability distributions. And the nice thing about the TVA, or like the property that we'll use, is that if you have two Gaussians with diagonal and homoscedastic covariance, you can show that, and you know that the centers of the Gaussian are at some distance, then you can show that the TVA between these two Gaussians is upper bounded by the TVA between a Gaussian centered at 0 with variance sigma square, and Gaussian centered at the distance between U1 and U2 with variance sigma square. So what this says is that basically, so how will we do that with DPSGD? Basically in DPSGD, U1 and U2 will be gradients of like the two processes. And we know that because they only differ by one sample, we know that the difference between U1 and U2 will be bounded in L2 norm. And what would be nice is if we were actually reaching this bound in L2 norm and we knew the direction, because then this step would just be equal to a Gaussian step. And this is exactly what this lemma 4 tells us, that we can sort of upper bound our case that has weird dependencies by an ideal case where every step is like pure Gaussian and doesn't really depend on the data. So the proof will consist in this. So we have a series of steps in our mechanism, and every time, and we'll make like changes to the transcript, and every change will only increase the total variation between the two distributions. So the first change will consist in changing the last step by a purely Gaussian step. And the second step will consist in reordering the transcript by putting the purely Gaussian step as the initial step instead of the last step. So the second thing is basically reordering. So we know that this will not change TV. And for the first step, it's based on lemma 4, but I will explain how we get to this. And so if we iterate that a bunch of times, we'll get to a state where all the steps are purely Gaussian. And so this total variation is like easier to compute. And it's an upper bound of the total variation for like SGM training. Okay, so this is the meat of the proof. And it's actually rather straightforward. So the total variation between the transcript on D and the transcript on D prime, it's the expectation on the it's the sum over, sorry, it's this sum over all transcripts of the probability of this transcript under X minus the probability of this transcript under Y. We can condition on this last step ST. And when we, so this is the second line, sorry, we do not condition, but we separate the sum. And we condition the, inside the probabilities, we can condition under the past S, so it's written as S lower than T minus 1. And so basically once, so if we do that, we basically have these two terms. They are conditioned on different pasts. So to sort of like mix these two terms together, we'll factor by one of the pasts. So we factor by the probability that X until T minus 1 is equal to S until T minus 1. And then the second term, the sum over ST of something, is actually a TVA, with A being equal to the ratio of the probability that Y until T minus 1 is equal to S until T minus 1, divided by the probability that X until T minus 1 is equal to S until T minus 1. So I don't know if there's any question on this at this point. But basically, this is like rather straightforward. And as we've identified this last bit to be the TVA, we can upper bound it by the TVA between two Gaussians. where one is centered at 0 and the other one is centered at the distance between these two distributions. And once we've done that, we can basically redo all the other steps to show that this is equal to the total variation between this new mechanism Ni and on D versus the mechanism on D prime. All right, so this is the main proof in our paper. And this shows the case without subsampling. And we can do a very similar thing with subsampling by noticing that, so with subsampling, with probability Q, we take the step, and with probability 1 minus Q, we sort of do the regular thing. So with subsampling, instead of X, we have this X prime. That's the mixture between Y with probability 1 minus Q and X with probability Q. And we can show that the TVA between X prime and Y is equal to Q TV of A plus Q minus 1 divided by Q between X and Y. And again, like the proof is sort of rather straightforward. Okay, so what we have done is to show that this total variation can be upper bounded by the total variation between two purely Gaussian mechanisms, but with this total variation between Gaussian mechanisms is not, to the best of my knowledge, there is no closed form formula for that. So we need to approximate it numerically. And fortunately, we can do that with Monte Carlo estimation. So the TV is equal to the integral over the universe of d mu minus d nu times indicator that d nu is lower than d mu. This can be factored. We can factor the d mu and we get 1 minus d nu over d mu, which is the expectation of 1 minus d nu over d mu, indicator of d nu lower than d mu. And this expectation is, so it's an expectation of a term that is between 0 and 1, because we know that this ratio here, so the indicator function ensures that the ratio is always lower than 1, so the quantity is always positive. And it's also always lower than 1 because the probabilities are positive. So we can estimate that by Monte Carlo by sampling a bunch of t's from distribution mu and computing the empirical average of this quantity. And because the quantity that we want to estimate is bounded, we can apply classical Hovding-Chernoff bounds. So finally, so this is, I guess, for the TV bound. And finally, we also need to compute KL divergence. But for that, we can still use the tools of Rényi differential privacy. So the Rényi divergence is this like complicated formula. And it's in particular, it's non-increasing in alpha. And we know that it's non-decreasing in alpha. And we know that when alpha goes to 1, the divergence go to the KL divergence. So in practice, what we do to estimate the KL divergence is we take alpha very close to 1. And this is like, there's not enough movement that we can estimate the KL sort of precisely. So we ran a bunch of experiments on CIFAR10 MNIST. And on these datasets, we compare the model accuracy to the advantage that is given by our bound versus Humphrey's bounds. So I guess our models have the same trade-off between noise and model accuracy that's like most models from the literature, but our gain is just in the translation of this amount of noise to an advantage. But this can be pretty significant here. in particular, we can see that for CFAR with we can be like sort of close to this 70% accuracy, while having a much lower advantage than the one that would be given by the previous best bound. All right. I don't know if I have time to go to a bonus. I had timed that for 40 minutes, which I guess we're at 40 minutes. So
you can continue. It's
okay.
It's fine.
Cool. So we can also get a bound for the like 1 minus delta worst case, which like is also interesting because it turns out that in practice this bound matches the previous best bound. So it means that it matches the Humphreys et al. Bound. So this Humphreys bound was the best for the average case accuracy. And in this paper, what we show is that our bound is better for the average case. And this previous bound still holds, but now with probability 1 minus delta. So how do we get that? So we know that if we have this DPSGD training, then with probability 1 minus delta, the log ratio of M of D equals theta versus M of D prime equals theta is between minus epsilon and epsilon. So that's slightly better than the traditional epsilon delta definition, but we have this property for DPSGD. And we can use Bayes' rule, which I wrote out here, but we can like basically skip to the last line. That's like the compact form of Bayes' rule that says that, so now the probability of D knowing theta is equal to the sigmoid of this log ratio. So that's like the nicer form of Bayes' rule. And we know that this, so we know that this log ratio is between minus epsilon and epsilon. And so, so yes, so this is like a classical binary classification problem, as I said earlier. And the accuracy is bounded by the max between the probability of D given theta and 1 minus probability of D given theta. So we can upper bound the accuracy by the max of sigmoid of epsilon, sigmoid of minus epsilon, and this max is equal to sigmoid of epsilon. So, and it turns out that this sigmoid function is very close to the bound that was given by Humphreys et al. All right, so what happens in real life? In real life, the so it can turn out that our model is more private than what we can analyze. So here our setup is very adversarial because we assume that we have access to the whole transcript of training. And we assume that sort of all gradients are trying to be adversarial. And in practice, some of these conditions will not be respected. For example, we can have that other elements of the data can hide individual contributions. This is the sort of like hide in the crowd phenomenon. It can also be that the norm of one sample's gradient is lower than the clipping threshold, in which case the sort of signal to noise ratio will be even lower. And I would say that this like average case versus worst case is a kind of a decision of the end user. So it depends on the privacy policy. I think in general, people prefer worst case guarantees. So, but I think it was very interesting to look at whether this particular setup in this like table of theory practice versus worst case average case, it was interesting to look at whether this particular case was close, and I'm sort of glad that it is. Cool. So that's all from my presentation. If you have any questions, happy to answer them.
I think, yeah, that was a great talk. Thanks, Alex. I think everyone's giving you a virtual clap. I think Saeed has a question in the chat. I don't know if Saeed, you want to unmute or?
Yeah, sure. Yeah, my question, thank you very much, Alex, for the very interesting talk. My question was, do you think these bounds could be improved for potentially more restricted adversaries? And what are some of these like meaningful restrictions that we can put on these adversaries?
Yes, it's a very good point. So I definitely think that these bounds can be improved. I think as practitioners, we sort of observe that it's often very hard to extract information from models, even though so we're able to do that in a lot of setups, but in real life setups where you train on tons of data, it's like much harder to extract information. So in particular, I think one difference between this work and the real life is this assumption that you can see the transcript of all gradients. So I think that if you restrict the adversary to only see, for example, the last model, you can probably get better bounds.
I have a question. So in your definition of advantage, you're essentially assuming kind of a uniform prior. So the game is basically I flip a fair coin. So what happens to your analysis if you flip a biased coin? Like your definition of advantage will differ, and does your analysis just like follow on with some like constant factor added to it, or like what would happen there?
That's a good question. So I think I think we looked at that initially. So I think if you have a biased prior, basically you might be able to leverage directly other bounds. In particular, I think you can probably let me go to this slide. You can probably use something like the bound from Kairos. That being said, so that should be one route. So I guess I don't know the answer, but there's definitely this route to get to a bound, and another one is probably, well,
I mean, my question is like your I guess like your definition of advantage will change, right? Because I mean, maybe I'm misinterpreting, but like you're kind of like hiding away like this prior, right? It just like it's half of something or other.
Yeah. That's so okay. That's definitely what's gonna happen. So I think you'll get something. You can probably rearrange the term to have something like to have a new advantage that's like instead of being a difference, there's like a coefficient between the second one. So I guess okay, I'm not entirely sure, but I would tend to say that it's probably can probably be written as a TVA if that's the case, and I would sort of assume that all the steps would work as well, but I'm not 100% sure. For example, there's one property of TV. Well, there's a couple of properties of TV that we are using. In particular, one that we're sort of using without explicitly writing so is the fact that the TV is like it's both the soup over the difference of probabilities and like half of the integral over the universe of the difference. So I don't think that would hold for TVA. So there's this kind of like details. I'm not sure whether they would work out, but yeah.
Okay. No, yeah, it's okay. Tinhao has another question. Do you need to TVA's result for Gaussian mixture for subsampling case?
So I'm assuming that the question is whether we need an equivalent
exactly.
of lemma.
This lemma 4.
Yes.
Yeah. Do you need to extend it for Gaussian case? For mixture Gaussian case?
Yes. Okay. That was my interpretation of the question. So you don't, because you directly have this result, which you can. So I haven't shown the full proof, but you can basically you can basically put that in the like. You can put that here. You can plug that here, and you will have the expected result. So you don't need to do another lemma 4, but for mixtures of Gaussian.
Because I think your X and Y here are a mixture of Gaussian.
Here they are.
Yeah, based on my understandings, like after you condition on off the previous step, but like for each step, it's your X and Y are both are still Gaussian mixture.
So I would tend to say that for each, at least, you mean the subsampling case? So in the subsampling case, one like the on. Yes. Okay, I see your point. But I think that the main thing is that okay, is your question about the fact that for the other samples of the batch, because we're comparing D versus D prime?
Yeah.
But actually, but it's not only for this Z prime that we're sampling it or not. It's also for all the other samples, right?
Yeah, exactly. That's why I think both X and Y are like a mixture.
Yes, but I think that what we are doing here is just basically bounding this. So the thing is that X and Y, apart from Z prime, they are mixtures, but of the same thing apart from this Z prime, right? So we are, I guess we're sort of like bounding uniformly, if that makes sense.
So you think like it's there should be some easy way to like it should be straightforward to like extend it to mixture case, right?
Yeah, I think so.
Okay. Yeah. Thanks. Yeah. I'm just like yeah. Thank you. Yeah.
Does anyone else have any questions? I'll give 10 seconds for people that are shy. Okay, I guess we can get 7 minutes back. Thanks again, Alex. That was really, really interesting stuff.
Thanks for inviting me. Yeah.
Always very good. Thanks, everyone. And yeah, the next talk will be, I guess, this time next week. So yeah, please join then. Cool.
Thanks. Bye-bye.
Bye-bye.